So section 7.4 goes over graphing rational functions. Rational functions, a ratio of polynomials, right? Rational numbers are a ratio of numbers, that is, numbers that can be written as a fraction. So here we're going to graph rational functions, so that is polynomials written as a fraction. Going to identify zeros and asymptotes, describe end behavior, and the domain and range. Before you can graph rational functions, you need to understand that there are 3 different points of discontinuity. Okay? They occur every time the 0 can be in a denominator, right? Every factor in the denominator could potentially be a point of discontinuity. F of x is not continuous at that point. Okay, so there are 3 types of discontinuity. One is removable. That is, the discontinuous piece of the graph can be removed to create a continuous function. So the graph will look like a normal graph, and then all of a sudden you'll have an open circle that is the whole of the graph. It occurs when a common factor is divided out. Non-removable discontinuities, mostly Algebra 2 will deal with asymptotes. The jumps in the graph we'll deal with when we talk about piecewise functions, and then you talk about again in pre-calculus. This happens when it's not divided out. So when you have factors in the denominator that are divided out, then they are holes in your graph. When you have factors in the denominator that do not divide out, they are asymptotes, which means they are not removable. You can't fix them. Graphically, this is a hole. This occurred because a factor divided out of the numerator and denominator. This is a jump. A jump happens when you're going along and all of a sudden you go somewhere else. So like wormhole, right? So the hole is like a sinkhole. You're driving down the road, all of a sudden sinkhole opens up. The road is gone at that point. It is an open circle, just like the open circles that you graphed when you did linear functions. Okay. But the road's fine on the other side, right? The graph, it continues like normal. It just has this hole in it. A jump is when you are on I-4, you get off at the Altamont exit, and all of a sudden you're at Disney, right? Teleportation. All of a sudden you're somewhere else. And then finally, C shows asymptotes. And those are the tourists who don't know what exit to get off, so they get off an exit because they think it's Disney. They see Disney, and they're driving right around Disney, but they can't reach it, right? That's an asymptote. So both jumps and asymptotes can't be fixed. So both jumps and asymptotes are non-removable because we cannot remove the discontinuity. Non-removable. A hole can be removed because we can say, okay, well that's the function, but then let's add in an additional point, and you can fill holes, right? You can fill holes. You can't bend a function to fill an asymptote. You can't connect this because then it wouldn't be a function, right? You can't do that. Any questions? So, let's graph a rational function. When we look at this function, the first thing we notice is that we have a x minus 1 in the denominator. This gives us our vertical asymptote. So we have a vertical asymptote at x minus 1 equals 0, which means x equals 1. So if x equals 1, we can draw our vertical asymptote right here. And x equals 1 is our vertical asymptote. To figure out our horizontal asymptote and all of our other points, the best thing to do is make an xy table, right? So we want to pick points that are fairly close to our asymptote, but we also want to pick points that are farther away to kind of get an idea of what's happening. So for this particular example, I'm going to pick -10, -5, -1, 0, 2, 4, 6, and 10. And I know that seems like a lot of points, but you'll see why we do that in a moment. Okay, so if we put in negative 10, right, we get negative 30 over negative 11, which is approximately, so this is approximately 2.72. If you put negative 5 in, we get negative 15 divided by negative 6, and that's approximately equal to, so that's 2.5. If I put negative 1 in, right, I get negative 3 over negative 2, which is 1.5. If I put in 0, I get 0. If I put in 2, I get 6 over 1, which is 6. If I put in 4, I get 12 over 3, which is 4. If I put in 6, I get 18 over 5, which is approximately what? 3.6. And then if I put in 10, I get 30 over 9, which is 3 1/3. We can go ahead and graph this, and we notice that at negative 10, we have about 2.7, right? So we're right here. Negative 5, we're at 2.5. At negative 1, we're at 1.5. At 0, we're 0. So we can see here that this graph, 2.5 is here. So we can see from this graph that it's going to go like this, right? And it looks like it's approaching a number, doesn't it? And so if we investigate further, we'll graph, let's see, 2, 6, right, is here. And 4, 4 is here. And 6, 3.6 is about here. And 10, 3 1/3. And it looks like it's getting super close to 3, right? Both of them are. And so we do a little bit of what I call bad algebra. So when we look at this function, we have y equals 3x over x minus 1. What happens as x approaches negative infinity? Or what happens as x approaches positive infinity? So if you take a moment and put in super huge values of x, so that is like 1,000,000, right? You have 3 times 1,000,000, right? So you have 3 million. And then you'll divide that by 1 less than 1,000,000. Does that 1 less really make a difference in the ratio? And the answer is not really, right? That minus 1 doesn't really make a difference. And so when we look at this ratio, we're really going to kind of ignore this minus 1 and think of this as 3x over x. And so when we get to super, super large values of x, because that minus 1 doesn't matter, that ratio for y is going to approach 3. That ratio for y is going to approach 3. Because that minus 1 doesn't really matter. So if you were to put in super, super huge values for x, like 1,000,000, right? You get 3 million over 2,999,999. That's really close to 3. Same with negative 1,000,000, right? You'd have negative 3 million over negative 3,000,001. Also a number very, very close to 3. So when we have this little number on the bottom that's not really making a difference, we notice that our y values are both going to approach 3. And so we actually have a horizontal asymptote here at 3. We'll talk a little bit more about it in just a moment. So if you're not quite sure what I'm talking about, give me a moment. So the horizontal asymptote at y equals 3. So our end behavior, as x approaches negative infinity, y is going to approach 3. And as x approaches positive infinity, y approaches 3. Our domain, and as we go all the way across here, right? We have x values that go from negative infinity to 1, and then 1 to infinity. And for our range, we have numbers that go from negative infinity all the way up to 3, and then 3 to infinity. Okay, let's do one more before we actually talk about this whole when to tell about a horizontal asymptote thing. So what's always the first thing we do? We have a polynomial, we have to do what with it? Factor it. So we have x minus 3 over x times x plus 2 all over x plus 1, and we're sad because we can't divide anything out. But we can identify a vertical asymptote, right? So we have a vertical asymptote at x plus 1 equals 0. So x equals negative 1. So we have our vertical asymptote at x equals negative 1. Okay, so if we want to use the same logic that we just used for that whole horizontal asymptote thing, and if we look at really, really large values of x, can we predict what the graph is going to do? So if we look at the standard form, not the factored form, if we look at the standard form, so x squared minus x minus 6 over x plus 1. When you're at 1,000,000, does adding 1 or subtracting 6 make a difference? Not really. So we can kind of think of this as x goes to infinity. So again, this isn't algebra, this is logic, right? We're thinking about this. We're saying, okay, 6 and 1 don't make much of a difference when we're adding and subtracting them from 1,000,000. So really we can kind of think of this graph as behaving like x squared minus x over x. That means that if x is 1,000,000, x squared is a lot bigger than that. So we end up with this super large number over this not as large number. Well, that's just going to keep getting bigger, isn't it? So there's no bound here. When the numerator is always bigger than the denominator, right? And the x values are just getting bigger and bigger and bigger, that means the value of the function is just going to keep getting bigger and bigger and bigger and bigger. And so there's what we call no bound. Or, in the words you want to hear, no horizontal asymptote. Because there is no value for y that is causing the function to go anywhere other than all the way up or all the way down. So in this particular function, as x goes to infinity, so as x goes to, or negative infinity first, right? As x goes to negative infinity, if we look at this function here, as x goes to negative infinity, we'll have some huge number squared, which is going to, or some huge negative number, well, really tiny technically, negative number squared, right? We square any negative, you're going to get a positive. You're going to subtract some stuff that's not going to make a difference, so it's still going to be positive. And then you're going to divide that by a less large but negative number, right? So we have a positive divided by a negative, which means y is going to approach negative infinity. As x goes to positive infinity, now we have a huge number squared divided by a not as large huge number. It's going to stay positive, and it's going to go to positive infinity. So, like all things, we need points, right? We have two types of points that are probably the easiest to find ever, like the y-intercept. At the y-intercept, x is always 0, so we can plug that in. So y equals 0 minus 6 over 1, right? 0 plus 1. So that's going to be negative 6. So I know 0, negative 6 is a point on my graph, and I can graph that right away. I can also find an x-intercept. X-intercepts are where y is 0. This is a fraction. Fractions are 0 when the numerators are 0. So if I look at these numerators right here, I can set them equal to 0 and find my x-intercepts. So x minus 3 equals 0, which means x equals 3, and 3, 0 is an x-intercept, and x plus 2 equals 0, which means x equals negative 2, and negative 2, 0 is also an x-intercept. So I have negative 2, 0, and 3, 0. Now, as I said before, we want at least 3 points on either side, right? Well, we have 3 points already, so that makes our xy table a little bit easier to find, right? So let's pick, I don't know, do you want negative 6? So we'll do negative 6. Negative 6 minus 3 is negative 9, times negative 6 plus 2 is negative 4, over negative 6 plus 1 is negative 5. So 36 over negative 5 is about 7.2, negative 7.2. So negative 6, negative 7.2 is approximately here. So it looks like it would help us to get a value that's in between negative 2 and negative 6. So let's pick negative 4. I'll do that in black, sorry. So negative 4. So negative 4 minus 3 is negative 7. Negative 7 times negative 2 over negative 4 plus 1 is negative 3, right? So negative 7 times negative 2 is 14. 14 divided by negative 3 is approximately, so we have negative 4.6, right? So negative 4, negative 4.6 is approximately here. So we can tell this graph is going to look something like this. Right? And then on the other side, it goes from here to here. So let's pick another value, so like maybe 6 or 8. So let's pick 6. Well, I started writing 8. We'll do 8. So 8 minus 3 is 5, right? 8 plus 2 is 10. 8 plus 1 is 9. So what's 50 divided by 9, which is approximately 0.5. So 50 divided by 9 is approximately 5.5. So we go out to 8 and go up to 5.5. And so you get a function that looks like that. So we have an asymptote with no horizontal, or we have a function with no horizontal asymptote, one vertical asymptote. So our domain is going to go from negative infinity to negative 1, and then negative 1 to infinity. And our range, if we look, there's no horizontal asymptote. So there are no values of y that we have to restrict. So our range is going to be negative infinity to infinity. Okay, so in general, graph the rational function, right, by factoring and simplifying first. Then we identified and drew all the asymptotes. The vertical asymptote, right, so the vertical asymptote, we got because we set the factors in the denominator equal to 0, right? Horizontal asymptotes we'll talk about in a minute. We identified and graphed any holes, and we haven't done an example of that yet, but we will in just a moment. Remember, the holes are when you divide out the common factors. That's when you divide out the common factors. Then we find and plot intercepts of the function, and then make a table so that we have at least 3 points on each section of the graph, right? So let's talk a little bit more about this horizontal asymptote stuff, right? So we just had a function where we had the numerator larger than the denominator. And that happened because we had y equals x squared over, and some stuff, right, over x. So that is the power of the top was bigger. And when the power of the top was bigger, that meant that the numerator kept getting bigger and bigger and bigger and bigger faster than the denominator. When that happens, we have no bound on the y values. Y is going to get bigger and bigger and bigger and bigger as x gets bigger and bigger and bigger, and so we have no horizontal asymptote. And that happens every single time the power is larger on top, because when the power is bigger, it overpowers the denominator. And so we get either much bigger negative numbers or much bigger positive numbers for y as x goes to infinity. When we had reciprocal functions, remember back, where you had y equals some x over like x squared, right? So that is the power of the bottom was bigger. So the power of the bottom is bigger. When that happens, when the bottom is bigger, we have a small number over a really, really, really big number. That is going to approach 0 because your horizontal asymptote will get close to 0. The other option is if the powers are equal. So that is, we have y equals some a x to the whatever over some b value of x to the whatever, right? So that is the exponents or the powers are equal. And when the exponents are equal, we end up with a horizontal asymptote that is the ratio of the coefficients, that is y equals a over b. So for example, in our first example, if we had had 3x over 2x, our horizontal asymptote would have been 3 over 2. Now, understanding how those functions work, right? Or fractions work. If the top is bigger, you have a bigger number. If the bottom is bigger, you're going to get closer to 0. If they're the same, their ratio will be the ratio of the coefficients in the front in standard form. It has to be in standard form. So there's one way to remember it if you want the mnemonic. How we just explained it is the best way for pre-calculus, because that is understanding how functions work and how fractions work. There is a mnemonic. It's if it's bigger on the bottom, the asymptote is 0. If it's bigger on the top, there's no asymptote. If the exponents are the same, you divide the coefficients. So Bobo Botten eats DC. Bobo Botten eats DC. Bigger on the bottom, your asymptote is 0. Bigger on the top, there's no asymptote because you are not bound. If the exponents are the same, you can divide the coefficients in front, the a, b, but it has to be in standard form. Let's do an example. Oh, don't forget to connect the points of each branch with a smooth curve. Real functions have curves, folks. No straight lines unless they're linear. So we always start with factoring, right? So we factor here, and we have x plus 1 over x plus 1 times x minus 4. So we identify our common factors, x plus 1 divided by x plus 1. And we use the factor that's left in the denominator to identify the vertical asymptote. So the vertical asymptote, x minus 4, should equal 0, which means x equals 4. So our vertical asymptote is x equals 4. And then we look to our coefficients to determine if we have our leading terms and our coefficients to determine if we have a horizontal asymptote, right? So it's bigger on the bottom, which means as x goes to negative infinity, y is going to go to 0 because we're going to have a small number over a really, really, really big number. So that means it's going to go to 0. As x goes to positive infinity, you're going to have a really, really small number over a really, really big number, so y is going to go to 0. Okay, so we know we have a horizontal asymptote at y equals 0, so we draw that in. Now we need to identify holes. We know that we were able to divide out x plus 1. So we have a hole at x plus 1 equals 0, which means we have a hole at x equals negative 1. But that's not a location. That's just a value for x. We know where on the function. Now we need to know what the value of the function is so that we can draw the hole. So we write the simplified function, and we plug the value for the hole into the simplified function, because that won't give us an error, right? If we plug it into the original function, it'll give 0 in the denominator, and that's a problem. So we plug in y equals 1 over negative 1 minus 4, which is negative 1/5. So we have a hole at negative 1, negative 1/5. And so we go to negative 1, negative 1/5, and we draw a hole right there. And we label it negative 1, negative 1/5, so that we know that that's a hole on the graph. Then we can identify our x and y intercepts. So our y-intercept happens when x equals 0. So if we plug in 0 for x, we get 1 over negative 4, right? So our y-intercept is 0, negative 1/4. So we go 0, negative 1/4 right there. So this means we really only need one more point over on the left-hand side, right? So let's pick one right next to the asymptote, so we'll pick negative 3. So 1 over negative 3 minus 4 is 1 over, or excuse me, not negative 3, positive 3. So 3 minus 4 is negative 1. So negative 1. So 3, negative 1. And we can see that this function is going to go like this. And there we go. Any questions about that? So then we need to find our x-intercepts, which we don't need to find because horizontal asymptote at y equals 0, right? So we're not going to have any intercepts there. So over on the other side, if x is 5, we have 1 over 5 minus 4, which is 1, right? So 5, 1. And then we can pick something else. So 7. So 1 over 7 minus 4 is 1/3. So 7, 1/3. And so we should probably pick like 4.5 because it seems like that'll give us a pretty picture of what's going on. So let's pick 4.5. So 1 over 1/2 is 2. So 4.52 is another point on our graph. And so we try to make a nice smooth curve that looks like that. Our domain is all x values that are not equal to 4, because remember, we are restricted at 4, and the hole. The hole happened at negative 1, right? So our domain is going to go from negative infinity to negative 1. Okay, so negative infinity to negative 1. Don't forget about the hole, because remember, the hole is a restriction in the domain, right? So negative infinity to negative 1, negative 1 to 4, and then union 4 to infinity. And then we have our range, and our range also has 2 points where it can't be equal. Because remember, this hole right here at negative 1/5. So our range is going to go from negative infinity to negative 1/5. Negative 1/5. Then from negative 1/5 to 0, and then 0 to infinity. Because remember, when you have a hole, and you have nothing else on the graph that will equal -1/5, that y value doesn't exist in your function. So it is restricted from the range as well. You need to make sure that you check both wholes and asymptotes when you are doing domain and range. You may have 3, 4, or 5 intervals for domain and range, so you need to keep an eye out for that.